Let us continue with the basics. Did you go through the basics last class we discussed? Last class basics. I think we stopped at orbitals. What are the shapes of different orbitals we have seen? S orbital, p orbital and d orbital. Okay. So just continuation of it. Suppose I start with s orbital. Let me take 1s. How many nodes are there? 0 nodes for any s orbital. Let me choose 1s or 2s or 3s. 0 nodes. So either I take plus or minus. It is immaterial. Either I can take totally plus or I can take totally minus. Okay. But what the answer that you have given is not correct. 1 0 1 2. Okay, for this the number of nodes are 0, for this the number of nodes are 1, and for this the number of nodes are 2. So previously you said all 0, but now some of you are saying 0 1 2. The number of nodes are increasing. So where is the node increasing? Then you should know what are the types of nodes. Node is a space where you don't find electron density. Okay, that is as simple as that. A node is a space where electron density is not found. Okay, or where there is a phase difference. Better to say where there is a phase difference. S orbital all is plus. So plus is not changing to minus. Plus and minus, if they change, then there is a node. For example, if I give you p orbital there is a plus slope and there is a minus slope. Plus to minus, there is a shift. There is a node. But in s orbital, everywhere it is the same wave function, so there is no node. But which node is that? Then we have two different types of nodes. One we call it as angular node, the another one we call it as radial node. Any orbital will definitely have an angular node, but radial node, that depends on its quantum number. Suppose if I take 1s, it is the first orbital, so it cannot have a radial node. Radial node means through radius. Angular node within the orbital. Radial node in between the orbitals. It is just like you have hydrogen bonding, intramolecular hydrogen bonding, intermolecular hydrogen bonding. In a similar way, you have two different types of nodes. One node is within the orbital, one node is between the orbitals. So if you find any node between the orbitals, it is radial node. If you find within, angular node. Okay, so just write a point. There are two types of nodes. These are angular nodes, and radial nodes. In simple terminology, this is within, radial node is between. One is within, one is between. So now let us come to the s, p and d orbitals. We are not going to discuss f orbitals. how many angular nodes? For s orbital, come in. For s orbital, just now we discussed 0. Angular nodes only, not total number of nodes. P orbital, 1 node. D orbital, 2 nodes. S orbital, all plus. P orbital, plus and minus. D orbital, plus plus minus minus. So wherever there is a phase difference, you can find a plane. In this there is no phase difference. In this there is a phase difference, plus and minus, so I find a nodal plane. In this case, between plus and minus and plus and minus, so there are 2 nodes. Okay, these are only angular nodes. Whatever I am speaking is about angular nodes. So S, P, D, 0, 1, 2. Suppose if I proceed, maybe if I proceed to F, G and H orbitals. F orbital is known, G and H, they are the next orbitals of F and G. So F, G, H, how many nodes you can expect? Just increase by 1. Okay, so 0, 1, 2, here you will be having 3, 4, 5. So you are just increasing by 1 node. You just note it. If I ask you a simple formula, how many angular nodes are there for a given orbital, how do you define? Then the number of angular nodes is equal to L. L means for s orbital, what is the L value? 0. For p orbital it is 1. So the number of angular nodes is equivalent to L value. That is simple. In detail these things will come in your quantum chemistry, but as basics of inorganic chemistry we have to touch a few simple things. Last class we discussed about few basics of quantum numbers, rules for the electron entry, shapes of orbitals. Today we are continuing with the nodes. We'll discuss multiplicity. Today in the first session we'll complete these basics. In the second session we'll go for the another basic unit, periodic table or periodic classification of elements. For some of you it might look like very basic periodic table, but we have to discuss periodic table. You should have an idea about all the basic elements and their classifications. Then we will enter into the mainstream units. Last class I asked a couple of questions. Did you get the answer? One question was why any orbital can accommodate only 2 electrons. Why not more than 2? Any answer? Okay, before answering it, let us understand about the nodes. We have seen angular nodes. Now let us see about radial nodes along the radius. So from the nucleus, the first shell, 1s orbital, 2s, I am drawing only s orbital. It will also have p, d, f and so on. But I am just drawing 1s, 2s, 3s and 4s. What change do you find? The change that you find is, suppose if this is green, yellow, green, yellow. If I draw 5s, that should be green. 6s should be yellow. What is the meaning of it? Meaning means, suppose if this is in plus phase, if all this wave function is plus, this will be minus. If this is plus, this will be minus. Plus, minus. That will alternate. It means wave functions will alternate. And wherever there is a change of wave function, we have a node. So here all is plus. Here all is minus. In between these two, there is a node. That node is called as a radial node. So for 1s, there is no radial node, but for 2s, there is one radial node. This is that radial node. It means this is the space where there is a phase difference, where you don't find electron density. The phase is changing from plus to minus. It is just like a wave. This is all plus. From plus, when it is changing to minus, what is the amplitude here? The amplitude is 0. All this is plus, all this is minus, the amplitude is 0. Likewise, all this is plus. From plus it is moving to minus. In between there will be no electron density. And that node is called as a radial node. For 1s there is no radial node. But for 2s, there is one radial node. If I ask for 3s, for 3s there is 1 and 2. For 4s, 1, 2 and 3. For ns, n minus 1. So for ns, n minus 1 radial nodes. Okay, you note this. You need not remember for each and every orbital, simply for ns, n minus 1. But remember, they will alternate always. 1s, 2s, 3s, 4s, wave function will alternate. Suppose if I draw p orbital, you are able to make the difference. One is plus, one is minus. Let me suppose this as 2s. Okay. If I draw 3s, how should I draw? This is 2s. In the center there is a nucleus. Center there will be a nucleus. So if this is 2p, just imagine this is 2p orbital. How is 3p? This is 3p, 4p, 5p. So what is the difference? If this is plus minus, just you take right hand as plus, left as minus. Plus minus, two lobes. This is for 2p. 3p will be like this. This will be minus, this will be plus. 4p, and that will alternate. So here if I give you 2p orbital, then this will be of 3p. 3p will be large. So if I draw 4p, 4p will be still larger. These two are of 4p, these two are of 3p, and these two are of 2p. Now you tell me, for 2p, how many radial nodes? No radial node for 2p, but between 2p and 3p, one radial node. Between 3p and 4p, one. But how many radial nodes for 4p? How many radial nodes for 4p? How many? 2. So this is 1. This is 2. So for 4p, 2 2, for 3p 1, for 2p nil. Okay, so how many total number of radial nodes for np? If I take np, n minus 2. Hope you got the logic now. I need not draw d orbital, we need not discuss f orbital. How many number of angular nodes for s? N minus 1. For p, n minus 2. Suppose if I give you d, that should be n minus 3, n minus 4 and so on. So we'll conclude. ns, np, is there any other formula for angular nodes? For radial nodes you gave a formula, it is equivalent to L. For angular nodes, for radial nodes, any formula? 2L, no. Any other formula? General formula, instead of remembering n minus 1, n minus 2, n minus 3, n minus 4, is there a general formula for angular nodes? Can I take this? Is it applicable or not? You check if it is applicable. N minus L minus 1. So let me take 3p orbitals. For 3p n minus 2, it means there should be one radial node for 3p. So n minus L minus 1. Suppose if I take 3p, how much is n? 3. L 1. For p orbital L is 1. 3 minus 1 minus 1. So it is 3 minus 2, it is 1. So this is a generalized formula. Every time you need not remember n minus 1, n minus 2, n minus 3, n minus 4. Instead, n minus L minus 1, where n represents principal quantum number, orbital quantum number. What is other name for orbital quantum number? Azimuthal quantum number. Okay, write down a question. Is this done? Complete it. I'll just give you a small question. You can see 2p is close to the nucleus. 3p, there will be little increase. I mean, it will go far away from the nucleus. And there will be a general question, which orbital's penetrating power is larger? Which one? S orbital. What could be the reason? Because nuclear, nearer to the nucleus. Okay, if I ask you 3s and 2p, who is nearer? Or I'll ask you 5s, 2p, who is nearer? 2p is nearer because it is in second shell, but 3s or 4s, it is farther. Then how do you explain? 1s is closer, that is okay, fine. But if you go for say 4s and then compare with 3p, then 3p is closer, third shell, 4s fourth shell. Then So if you just compare s orbital, p orbital and d orbital, look at the diffusion. S orbital is spherical in shape. It is distributed all over the space. It means just imagine a nucleus. Around this nucleus, s orbital is found everywhere. Around the nucleus, everywhere it is found. But p orbital, lobes. It is like lobes. Above, below, towards right and left, towards you and away from you. In between there are spaces. So electron density is not fully occupied. And if you go to d orbital, 4 lobes. Just for one orbital there are 4 lobes. Diffused, or the rate of diffusion increases. Diffusion means not your physical chemistry diffusion. We call diffused orbitals. D orbitals are diffused orbitals because electron density is completely diffused. Okay, p orbital little bit diffused, but s orbital it is very compact. So everywhere it is like electron density. Therefore we say its penetrating power towards nucleus is also high. But p orbitals there are spaces. D orbital more spaces. Therefore its penetrating power will reduce. So that is how we explain the penetrating power. In general we give penetrating power. You just note down the sequence of penetrating power. This will come in your periodic table. Penetrating power of orbitals. Organic chemistry also this will be useful. And this will be useful for your Moss bar. In Moss bar spectroscopy we consider only s electron density. Everything we relate it to s electron density because the penetrating power of s electron density is more. Okay, now write a question. Supposing that the spin of an electron is 1. Supposing that the spin of an electron is 1, comma, how many electrons can be accommodated? How many electrons can be accommodated in 1s orbital? How many electrons can be accommodated in 1s orbital? Last class, whatever question that I have asked you, why every orbital can take up only 2 electrons. Now I have asked another question. The answer for that question is in this question. So understand this question carefully. If you can understand this question, the answer for that question will come. Spin angular momentum. But how many electrons can be put into 1s? 2. Okay. If I take 1s orbital, I can put a maximum of 2 electrons. Okay. So last class my question was, suppose if I take a 2s orbital, or maybe I take a 3s orbital, space is increasing, but why does it take only 2 electrons? Now the answer is, the spin of an electron is 1 by 2. Because the spin of electron is 1 by 2, it has the maximum of 2 orientations only. How do you get these orientations? Through a formula called as spin multiplicity. This we discussed. What is spin multiplicity? Two s plus 1. So if I am giving you 1 electron, what is the spin of that 1 electron? 1 by 2. It means whenever I give you an electron with a spin of 1 by 2, it can have a maximum orientation of 2 only. It can be oriented in only 2 directions. What are those 2 directions? Suppose if this is one direction, up spin, the another one is down spin. It cannot have any other orientation. Quantum mechanically it is impossible. It is just like if I am an electron having a spin of 1 by 2. I can stand like this, or I can do Shirsasan. But I cannot sleep. I cannot be in this position, I cannot be in this position, I cannot be in this position. Only 2 positions for me, 1, 2. But if the spin is 1, suppose I am giving a spin of 1 to an electron, then how much is the multiplicity? Suppose if I give spin of 1, then there are 3 orientations. That same electron can have 3 orientations now. So 3 orientations means if this is 1, this will be 2, this will be 3. Then an orbital can take up 3 electrons. So to the question that I have asked yesterday, why only 2 electrons can fill up an orbital? Because its spin is only 1 by 2. But if I can change the spin of an electron, according to the spin, I can accommodate the number of electrons in a given orbital. If the spin is 1, I can accommodate 3 electrons. And what does Pauli exclusion principle say? No 2 electrons should occupy the same quantum space. This is occupying this type of space. Next one is occupying this space. Third one is occupying like this. 3 are different. No 2 should be same. But if the spin is 1 by 2, either up or down, if I put the third electron, again it has to go as up, or it has to go as down. 2 up, not allowed. But if the spin is 1, then you got a new orientation. Then I can accommodate 3 electrons. Okay? If I want to accommodate 4 electrons, then what should be the spin of the electron? If I want to put 4 electrons in an orbital, in a single orbital, what should be the spin of an electron? How much? It means I want 4, 2 into s plus 1. This should equal to 4. How much is s? So 2s is equal to 4 minus 1. 2s is equal to 3. S is equal to 3 by 2. If the spin of electron is 3 by 2, then I can accommodate 4 electrons. It means those 4 electrons will be like this. 1, 2, 3, 4. Two, 3, 4. If this is 1, this will be like 2, this will be 3, and this will be 4. These things will come in your quantum. Okay? But this is a different question. This question will not come, but these related things will come. So now did you understand why an orbital can accommodate only 2 electrons? Because its spin is only 1 by 2. It has a maximum of 2 orientations only, either up or down. But if I can change the spin of an electron, the number of electrons that I can put in an orbital can also be increased. Just add a note. Any orbital can take up 2 electrons only. Any orbital can take up only 2 electrons. Any orbital can take up only 2 electrons because the spin of any electron is 1 by 2. The spin of any electron is 1 by 2. Therefore, the number of possible orientations are 2s plus 1 are 2s plus 1, it means 2 into half plus 1, 2 into half plus 1, 2. 2 into half plus 1, 2. To give you a better clarity, I am just taking 4 different electrons. Tell me the maximum spin for one electron. Maximum spin means we have to always take in positives. So maximum spin will be 1 by 2. If there are 2 electrons, what is the maximum spin? 1. Up and up. There could be up and down, but that is a combination. We have to take maximum spin. Next, if it is 3, 3 by 2, 4, 2. Then what is the spin multiplicity? 2 into s plus 1, 2 into half plus 1. This is 2, 3, 4 and 5. It means if there is one electron, how many possible orientations? 2 orientations. What are they? Up or down. If there are 2 electrons, how many possible orientations for those 2 electrons? 3 possible orientations. What are they? Both up and down, down and down. If I put down and up also, it is just one and the same, right? But that is a possibility. Up and up, only one possibility. Down and down, only one possibility. But one up, one down, 2 possibilities. Up, down, down, up. Okay? In your NMR, you will be getting 1:2:1 intensity ratio. Peaks. How do you get 1:2:1? This is how you get 1:2:1. Suppose there are 3 electrons. How many possible orientations? 4 possible orientations. What are they? All 3 could be up, 2 up, 1 down, 1 up, 2 down, all 3 down. Then what is the intensity for your NMR spectroscopy? 1:3:3:1. How do you get 1:3:3:1? 2 up, 1 down, 2 up, 1 down, 2 up, 1 down. 3 possibilities. With 2 up, 1 down, 3 possibilities. 1 up, 2 down, 1 up, 2 down, 1 up, 2 down. So these are the various possibilities. You get 1:3:3:1 in your spectroscopy. For this you get only 1:2:1 intensity. I am talking about intensity, not the number of peaks. So this is intensity. Presently it is not needed. And finally 4 electrons. How many orientations should I get? 5 orientations should I get? All up, 3 up, 1 down, 2 up, 2 down, 1 up, 3 down, and all down. Note down this table. What are these multiplicities? Last class I gave you doublet, triplet, quartet, quintet or pentet. Spin multiplicity, what is the importance means? It gives you an idea about the possible orientations. This is the meaning of spin multiplicity. Electron spin multiplicity, to be specific, because there could be nuclear spin multiplicity also. That is also similar, 2i plus 1. If there are n number of nuclei, then 2ni plus 1. In your NMR it will come 2ni plus 1. Electron spin multiplicity. It gives an idea about the possible orientations of the given electrons. This is what we have done. It gives an idea about the possible orientations. Completed. I'll give you a very short correlation between the orbitals. You are aware of molecular orbital. We will be studying all those molecular orbital theories in chemical bonding. But suppose if I take atomic orbital, I am taking S, P, D, F. I am taking atomic term symbol. Term symbols will come in electronic spectroscopy. Don't get confused now. Just take it as basics. These come in capitals. Term symbol or terms are energy levels that define a particular configuration. So for sp-df orbitals, you have sp-df terms. These are in capitals. You just note down. Explanation will come in electronic spectroscopy. Why am I giving is just to bring a correlation. Suppose if I ask you molecular orbital, what are the various molecular orbital symbolisms? Sigma, pi, delta, phi. These are molecular orbitals. When atomic orbitals combine, they give molecular orbitals. Then what are the molecular term symbols? Molecular term symbols are sigma, pi, delta, phi. In Greek alphabets, alpha, beta, gamma, delta, just as you have English alphabets, these alphabets are uppercase, these are lowercase. So in a similar way, even in Greek you have uppercase alphabets and lowercase alphabets. Suppose if I take pi, this is a lowercase, uppercase. Or if I take delta, small letter, capital letter, what we call it as lowercase, uppercase. So small letter, this is how we have tried delta. Capital delta is this. Small phi, capital phi. Small pi, capital pi. Small sigma, capital sigma. What correlation can you see in all of them? What correlation can you see? I have correlated atomic orbitals with atomic term symbols or different energy levels, molecular orbitals with molecular term symbols. What is the correlation between these atomic and molecular symbols? Sigma. Okay, pronounce this. S. S. But how do you start with? S. Sigma. S. S. Next one. P. This is P means P. D. And this is F. So that is how they correlated. F orbital, F term symbol. F molecular orbital, 5 molecular orbital, 5 term symbol, all are correlated. Okay, S, P, D, F. You may think, what should I do if I correlate them? But scientists, they are scientists. Future, some of you will become scientists in industries. You will be putting some different codes, correlations will be there. These things are basics for you. How to correlate things. Completed? Now finally let us discuss about the formation of various orbitals, molecular orbitals and their combinations. Formation of bonds. First one, sigma bond. So here itself I am giving you basics. When I go to chemical bonding, we'll directly discuss about sigma bond, directly about pi bond. Basics here itself I am giving you. When does a sigma bond form? Or what type of overlap? Head-on overlap we say, or linear overlap. Head-to-head overlap or linear overlap. So just write down that one point. Head-to-head overlap or linear overlap. Head-to-head overlap or linear overlap. Second point, these bonds are formed from the combination of those orbitals where h by 2 pi orbital angular momentum value will be 0. Okay, note down. These orbitals means molecular orbitals, which we are relating it to bonds, sigma bonds. These molecular orbitals are formed. These molecular orbitals are formed from the combination of these molecular orbitals are formed from the combination of those atomic orbitals of those atomic orbitals whose h by 2 pi orbital angular momentum, in future you just abbreviate it as OAM, h by 2 pi orbital angular momentum values, h by 2 pi orbital angular momentum values are 0. So which orbitals have h by 2 pi orbital angular momentum value 0? In the last class we have seen s orbital, it was having 0, pz was having 0, dz square was having 0. It means only these three orbitals can form sigma bond. No other orbital can form sigma bond. So h by 2 pi optical angular momentum value 0. It is with s orbital, pz and dz square. Only these three orbitals can involve in sigma bond. Simple to remember. No other orbital. Out of 1s, 3p and 5d orbitals, 9 orbitals, 3 orbitals are involved for sigma bond. What are the various combinations? Note down the combinations. First one, an s orbital can combine with s orbital to give you sigma, or s orbital can combine with pz, or s orbital can combine with dz square. Suppose if I give you s orbital and another s orbital, or I can give you s orbital and a p orbital. We say symmetry allowed combination. Symmetry allowed combination means, suppose if I take s orbital can they form a sigma bond? S and pz? No. Symmetry has to allow the combination. Symmetry has to allow means this is S, this is pz. But if this is plus, this should also be plus. But here you can see this is minus. Plus plus should match. Though if it is pz, then pz has to orient itself properly. So here you can see yellow to yellow, yellow to yellow, yellow to yellow. Green is other phase. Green is other phase. So symmetry has to match plus to plus or minus to minus, but not plus with minus. So if this is minus, this is plus, not matching. Symmetry has to match. Though it is pz, symmetry should match. Any other combination, S with S, S with pz, S with dz square can give you sigma. All S combinations are done. Now let me take pz with pz, pz with dz square, dz square with dz square. These many combinations for sigma bond formation. Pz with pz means this is pz and pz. Plus to plus should match. Then pz with dz square. Plus to plus or minus to minus, whatever you think. But both signs should be same. Plus to plus and minus to minus has to match. And lastly, dz square with dz square. S atomic orbital has how many nodes? Just angular nodes. S atomic orbital 0. S sigma correlate atomic orbital with molecular orbital. S atomic orbital, how many angular nodes? 0. Then sigma molecular orbital, how many nodes? That should also be 0. Sigma, there should be 0. Let us check. This is S and S. Plus and plus are combining. In between, in the internuclear axis, do you have any phase difference? In the internuclear axis. Internuclear axis means in the center there is a nucleus, in the center there is a nucleus, these two are combining. Along this internuclear axis, do you have any nodal plane? Yes or no? Do you have a nodal plane? No. S and P, do you have a nodal plane? Yes or no? Yes. Do you have a plane here? So how many nodes are there for this sigma? 0. S orbital 0. So sigma should also have 0. This is not the node we require. There is a statement just now I have given. Between the internuclear axis, you should not find a node. Internuclear axis. Where is the nucleus? This is the nucleus. Where is the nucleus? This is the nucleus. Between the nucleus, do you have a node? No. This is angular node of p orbital, not a sigma bond. Within the sigma bond, do you have or not? That is what we are checking. Okay? Not in the individual orbital. Let us check. S and dz square. Do you have any node? No. Because in the center there is a nucleus. In the center there is a nucleus. Between this, is there any node? Any phase difference? No. Pz, Pz. Here there is a node. Here there is a node individually. But look at the internuclear distance. This is the nucleus. This is the nucleus. Between the internuclear distance, do you have any change of sign? No. If this is plus, this is also plus. If this is plus, this is also plus. So along the internuclear axis, there will be no node. That is a sigma bond. This is just at a higher level understanding. For any sigma molecular orbital, there will be no node. Okay? Note down that point. Along the internuclear axis of any sigma bond combination along the internuclear axis of any sigma bond combination, comma, the number of nodes are 0. The number of nodes are 0. Okay? Now everyone, just imagine yourself that you are watching this combination from this side. Just imagine yourself, you are watching these combinations from this side. Okay? When you are watching the combinations from this side, this is your eye. You are watching it from here and you try to rotate it. This is your orbital combination, you are trying to rotate it. While trying to rotate, is there any change of sign? No. Because if this is plus, everything is like plus only. If this is plus, everything is like plus. If this is plus or minus, everything is minus. Everything is minus. Everything is plus. So while you rotate by 360 degree, is there any change of sign? No. That is a sigma bond. Got it? One more definition. While you are rotating it by 360 degree, there will be no change of sign. That is a sigma bond. Okay? If these combinations are done, we'll go for pi bond. These points you can maybe running notes or however you want to write. When you are looking it from a side and if you are rotating by 360 degree, there is no change of sign. So that indicates it is a sigma bond. How do you define a pi bond? Head-to-head overlap, linear overlap is sigma bond. Pi bond, sideway overlap. If these are the two orbitals, head-to-head overlap is sigma. Sideway overlap, pi. So pi is sideway overlap. Second point. Pi bond is formed from the combination of orbitals whose h by 2 pi orbital angular momentum value is how much? Last class we discussed. Whatever orbital you choose, it should have either plus or minus 1 h by 2 pi angular momentum. Either it should be clockwise 1 or anti-clockwise 1, but it should be 1. Which orbitals? Px, Py, dxz, dyz. No other orbitals. So only these orbitals can form pi bond. Simple. Px, Py, dxz, dyz. What are the combinations possible? A Px can combine with a Px. A Py can combine with a Py. Px and Py cannot combine. Px and Py cannot combine. But Px can combine, Py can combine. Suppose if this is Px. Sideway overlap. Py. Say this is towards you. Sideway overlap. Between the internuclear axis, do you find any node? Yes, you find it. Where do you find it? Let me check. If this is nucleus, this is the internuclear axis. This is nucleus, this is the internuclear axis. So above is plus, below is minus. So between the internuclear axis there is one node. Between the internuclear axis there is one node. Whatever combination you take, you will get only one node. Okay? That is a pi bond. Px plus Py will not give. Look from a side and try to rotate by 360 degree. How many times there is a change of sign? One time there is a change of sign, because if this is plus and minus, at 180 plus is coming below. It means once there is a change of sign. So that is a pi bond. Remember, okay? Once there is a change. For sigma, no change. Px, Py. Third combination, Px with dxz. Py with dyz. That day I told you, common coordinate, they can combine. X common coordinate should be present. Py common coordinate should be present, but not Px cannot combine with dyz. Py cannot combine with dxz. This can give you, for these two I am just drawing only one diagram, you try to understand. Say if this is Px, or you may take it as Py, just one diagram, okay? Then either dxz or dyz. Now look at the internuclear axis. Along the internuclear axis, how many nodes? One node. This is internuclear axis. One node is present. So whatever may be the combination, you will get one node. Dxz, dyz can't give. For these two, just a single representation I am putting. If this is one lobe, between the internuclear axis only one node can be found. So any combination will give you one node. How many combinations are valid? Forget about invalid. 1, 2, 3, 4, 5, 6. Only 6 combinations are valid. Remaining are invalid. Symmetry must match, remember. Suppose if they give you this type of combination, this is dxz, this is also dxz. Can they combine? In this way, can they combine? No, because if this is plus, this is minus. So combination is not possible. They can't combine. Then this has to orient itself. It has to orient itself so that it will match. Then combination is allowed. Otherwise, it will not. So for that adjustment, it will take some energy. Some energy will be taken up. That will come in your reaction mechanism, inorganic reaction mechanism. There are some reorganization energies, solvent reorganization, bond reorganization energy, and so on. So wherever you have matching symmetries, only there bond can be formed. In chemical bonding, you might have heard about word linear combination of atomic orbitals, LCAO method. But at higher level, we use a word symmetry allowed linear combinations. Symmetry has to allow. If it is in this way, symmetry doesn't allow. But if it is in this way, symmetry will allow. Completed? This is sigma and pi. Last combination is delta. How does delta bond form? only two orbitals. This will come in your metal clusters and organometallic chemistry. Which orbital is involved in the quadruple bond of Re2Cl8 minus? Which d orbital is involved, or different questions? Completed. So which orbitals can combine? dxy with dxy, eclipsed overlap. If these two are above and below, these two are like towards you and away from you. These two combine, these two combine, these two and these two. So along the internuclear axis, how many nodes can you see? Two nodes. Along the internuclear axis you will find two nodes. If this is one nucleus, this is another nucleus, there will be two nodes. Just once I am showing. Suppose I take this as a dxy. Okay. Imagine this is another dxy orbital. Plus to plus, plus to plus, minus to minus, minus to minus. All four lobes of one orbital overlap with all four lobes of other orbital. Okay. If it is head to head overlap, sigma bond. Sideway overlap, pi bond. If it is eclipsed overlap, delta bond. So if this is the internuclear axis, now you can check along the internuclear axis how many nodes are there. This is one node, this is second node, two nodes. Suppose if it is a pi bond, this is the internuclear axis. Along the internuclear axis there is only one node. If this is plus, this will be minus. Forget about these lobes. This is internuclear axis. Consider only internuclear axis. And for sigma, internuclear axis, no node. So 0, 1 and this is 2. Okay, these are the sigma, pi and delta combinations. When you are looking it from a side, while you rotate, how many times there is a change of sign? 2 times. There will be change of sign 2 times. Suppose this is the combination. You are looking it from the side. Now you can check. Once there is a change of sign. Second there is a change of sign. Twice there is a change of sign. So we say there are two nodes. Write a question. How many nodes can be seen? How many nodes can be seen for pi ABMO ABMO, anti-bonding molecular orbital. How many nodes can be seen for pi ABMO? Any answer? Pi ABMO. Pi ABMO means pi star. How many? You just increase by 1. Remember, between bonding and between anti-bonding, the number of nodes will increase by 1 unit. So sigma bonding 0, sigma anti-bonding will be 1, pi 1, pi star will be 2. Those are the number of nodes. Suppose that if this is pi bond combination, for pi bond combination sideway overlap, if it is pi star, this is pi star, they move away. So along the internuclear axis, here there is one node, here there is second node. Did you notice it? Suppose if this is the combination plus to plus, minus to minus, then there is only one node. Here there is no node. Between the internuclear axis there is no node here. Plus plus, minus minus, no node. But if the combination is like this, then here there is a node, here there is a node. Two nodes. This is pi star. Pi star combination will be like this. Plus minus, minus plus. Plus plus, plus plus, sorry, plus minus, bonding. Plus minus, minus plus, anti-bonding. So always one node will increase. Right, we'll close with the last basic point. Suppose if I give you s orbital, p orbital, d orbital and f orbital, which of them will have inversion? Which of them will have inversion? F orbital anyway we can't draw, so based on SPD, let us check. Suppose this is the nucleus present in the center. Everywhere it is like plus. Same sign. You should know what is inversion. Inversion is a symmetry element. It will come in symmetry. Okay. What is inversion means? Starting from the center point called as center of gravity, whenever I draw a line, if it meets a point, if I extend the line in the opposite direction to the same distance, it has to meet an identical point. Then we say inversion is present. Okay, I'll just show an example. Suppose I'm showing you this. Starting from the center, if I draw a line, it is meeting a point. The same line, if I extend it in the opposite direction to the same distance, it has to meet identical point. So from here, if I draw, it is meeting white. I am extending the line in the opposite direction to the same distance, it is meeting green. Now do I have inversion? No, it is absent. But suppose if I take this, starting from the center, I draw a line, it is meeting a point. I extend the line in the opposite direction to the same distance, if it is meeting an identical point, then I say inversion is present. So do I have inversion? Yes. It means in this inversion is present, in this inversion is absent. I am checking the same for the orbitals also. If I choose an s orbital, does s orbital has inversion? No. Why not? Because starting from the center, if this is the center nucleus, I draw a line, it is meeting plus. Wave function is plus. Opposite direction to the same distance also it is meeting plus. I am drawing a line, it is meeting plus. Opposite direction plus. Everywhere I go it is plus only. So do I have inversion? S orbital has inversion. Let it be 1s, 2s, 3s. S orbital has inversion. If I draw p orbital, for this p orbital starting from the center, I draw a line. When I draw a line, is it meeting identical points in the opposite directions? From the center I am drawing a line, it is meeting say plus. I extend the line in the opposite direction to the same distance. It is meeting minus. This is meeting minus. So do you have inversion? Inversion is absent. Let me take d orbital. From the center I draw a line meeting plus, opposite direction meeting plus. From the center I draw a line meeting minus, opposite direction meeting minus. So do you have inversion? Yes. And if I choose f orbital, it will not have. That will alternate. Simply it will alternate. So inversion is present, absent, present, absent. GH, if I put, it will be present, it will be absent. If I just extend to GH, it will be present and absent. What is parity? Parity means you have to check whether it is totally even or is it odd. Is the parity even or is the parity odd? That is what you have to check. Even parity, everywhere it is like plus plus, even. One side plus, one side minus. It is odd. So s orbital, everywhere it is plus. So we call it as even parity. Parity is even. But for p orbital, it is odd. One side it is plus, the other side it is minus sign, therefore we call it as odd. D orbital we call even. Why is it even? Because inversion is present, plus plus, minus minus. So minus to minus, plus to plus, everywhere it is like even. And f orbital will be odd. They will alternate. G orbital will be even. H orbital will be odd. What is the name that you give when parity is even? Whenever parity is even, we give a name. Gerade. Ungerade. This will continue. Gu symbol which you give in chemical bonding, that is gerade, ungerade. Gerade means parity will be even, center of inversion is present. Ungerade means parity will be odd, center of inversion will be absent. In some universities they pronounce it as garade, ungarade. They just pronounce it as garade. We call it as gerade, but they pronounce it as garade in some foreign universities. And we call it as un, they call it as un. This is actually un, un is un, but we call un. So we call ungerade, they call un, ungarade. So you just try to remember and go through all these basics. We'll take a very short break of 5 minutes, then we'll come up with a new unit, periodic table. Today it will be introductory part. Trends in the next class we'll discuss, but today we'll just go through what are the various postulates that have been come forward in the first first era of periodic table classification, different types of classification, names of scientists, the rules that they have proposed. It is 6:25. We'll meet again by 6:30.